Hello, welcome back to Digital Urim. In the previous videos, we learned how basic Linux permissions work. We saw what R, W, and X mean. We learned that R means read, W means write, and X means execute for files. We also learned that in directories, the X permission has a special meaning. It allows a user to enter or traverse that directory. We learned how to read permissions like 755, 644, and 777. And we saw that those numbers are not random. They are part of octal notation. But now we are going one level deeper. Because Linux does not only have basic permissions, Linux also has special permissions. And these special permissions are fundamental for understanding how certain internal mechanisms of the operating system work. Today, we will begin with one of the most important special permissions, SUID. SUID means Set User ID. The name may sound technical at first, but the main idea is very clear. SUID allows a program to run with the permissions of the file owner, not necessarily with the permissions of the user who executes it. That sentence is very important, so let's say it another way. Normally, when a user runs a program, that program runs with the permissions of that user. But when a program has SUID enabled, it can run with the permissions of the file owner. And if the file owner is root, then that program may perform certain actions with root privileges. This may sound dangerous, and in some cases it can be, but SUID also has legitimate uses inside the system. A classic example is the command password. When a user changes their password in Linux, the system needs to update protected information. That information should not be directly modified by any normal user. So an important question appears. How can a normal user change their own password if the files related to passwords are protected? The answer is SUID. The password program can have SUID enabled so it can perform a specific task with controlled privileges. This allows the user to change their password without giving them full access to the system. This is a legitimate example. SUID does not exist to break security. It exists to allow certain necessary operations in a controlled way. But now comes the important part for cybersecurity. The real risk appears when a program with SUID belongs to root and also has a vulnerability or an insecure configuration. If that program fails, the attacker does not only compromise the program, they may be able to make their code run with the privileges of the file owner. And if the owner is root, the impact can be full control of the system. For example, imagine a program with SUID that is owned by root. That program runs with elevated privileges. If the program allows external commands to be executed insecurely, validates input poorly, or has a memory vulnerability, an attacker may abuse that behavior. The problem is not only that the program fails. The problem is that it fails while running with higher privileges. That is the critical difference. A failure in a normal program can be serious, but a failure in an SUID program owned by root can be much more dangerous. That is why, in security, SUID always deserves attention. Not because every SUID file is bad, but because SUID changes the privilege context. Now let's connect this with the octal notation we learned in the previous video. In basic permissions, we saw numbers like 755, 644, 777. Each number represents permissions for the owner, the group, and others. But special permissions add a fourth digit at the beginning. SUID has the value 4. That means if we see a permission like 4755, that initial 4 tells us that SUID is enabled. And the other three numbers, 755, represent the normal permissions of the file. This detail is very important because in Linux, a single digit at the beginning can completely change the security meaning of a file. A file with permissions 755 may be normal, but a file with permissions 4755 has SUID enabled, and that means we need to review it more carefully. Now let's see how SUID appears in the output of ls-l. Normally, you may see a file with permissions like this, -rwx-r-x-r-x. Remember that the first character indicates the file type. The dash means it is a regular file. After that, we see the permissions for the owner, the group, and others. But when SUID is enabled, we will see an S in the position where the owner's X would normally appear. For example, -rwsr-xr-x. Look at the first permission section after the file type, RWS. That S indicates that SUID is enabled. It means that this program has special behavior related to the owner of the file. If the owner is root, that program may run with root privileges, even if it is launched by a normal user. Here is an important technical detail. If you see a lowercase s, it means SUID is enabled and execute permission is also present. But if you see an uppercase S, it means SUID is enabled, but the execute permission is missing. That usually indicates a strange or incorrect configuration, because SUID without execution normally does not serve its purpose. This type of detail is important for an analyst. A single letter can change the entire interpretation. Up to this point, this first part is complete. Today, you learned what special permissions are in Linux, and we focused on SUID. You learned that SUID allows a program to run with the permissions of the file owner, not necessarily with the permissions of the user who executes it. You also learned that SUID is represented in octal notation with a 4 at the beginning, as in 4755. And you learned how to identify it in the terminal with an S in the position where the owner's X would normally appear. But the most important idea is this. If an SUID program is owned by root and contains a vulnerability, the impact can be very serious. In the second part, we will continue with the other two special permissions, SGID and StickyBit. We will see how special permissions related to groups and shared directories work, and why they are also important for cybersecurity. See you in part 2. Understand, defend, grow.